Welcome to the Fall 2022 CODESYS Tech Talk. Today I will be introducing the concept of object-oriented I/O. But before we go through object-oriented I/O, let's discuss some background, new concepts, and a quick review of object-oriented industrial programming. So CODESYS has three areas where it lacks complete support for object-based programming. The first is alarming. Fortunately, we have a workaround for that. The ControlSphere OOIP library allows objects to declare and define their own alarms. The alarms for each instance just show up in the alarm tables. No need to create or maintain lengthy alarm lists. The next is persistence, parameters, and recipes. The ControlSphere CPP library provides object-based methods to handle persistence, parameter, and recipes. Again, for every new instance of a function block you declare, its persistence, parameters, and recipe variables are all handled. No lists to create or maintain. The third is I/O, and I'll use the rest of our time together today to show a solution for that. Now, there are three cognitive leaps I'm going to ask you to make throughout this presentation. The first is the I/O modules are just another piece of equipment. No different than a motor, a valve, a proximity switch, or any other piece of equipment in your plant or machine. I/O modules should be treated just like any other piece of equipment. Consistency promotes simplicity. The second is I/O mapping is just another equipment parameter. The equipment specifies the I/O mapping just like it specifies its pulses per liter or its high-level alarm set point. And the third is you can live without the CODESYS I/O tree. I know that sounds like a radical concept, but it can be done. I mean, if you really look at it, the CODESYS I/O tree is great for beginners and small projects. I mean, it's GUI based, so it really leads you through how to configure your I/O if you're not already familiar with that. But it becomes very cumbersome and time consuming for larger projects. The CODESYS I/O tree and all the complexity and maintenance requires can be eliminated. So no more millions of mouse clickies to manually configure each I/O point or write and maintain some Excel macros or any of the other tricks we used to play to make the CODESYS I/O tree work for large designs. So for anyone who hasn't seen my videos on object-oriented industrial programming, let me run through a quick review. Object-oriented industrial programming is a term I coined to refer to the easy subset of full object-oriented programming. Easily learned on the job, no 4-year computer science degree required. OOIP provides like 80% of the benefit with only like 20% of the complexity. So personally, I feel object-oriented industrial programming is the future of industrial controls programming, and those who adopt it first are first to begin to reap the benefits and the large productivity and reliability improvements it provides. We had a good presentation earlier this week from Dominique Girard and Russ Rupkin showing solid examples of OOIP. Of course, the competition to CODESYS will say OOIP is a fad and not worth the effort learning it. They'll say that at least until their development system catches up. That's just the way things work. Anyway, the object of object-oriented industrial programming is to build your design from self-contained, self-reliant objects that match the objects in your plant or machine. So here we have an example of a little material processing plant with 4 analog sensors, horsepower, level, temperature, and pressure, 2 motors, and 2 valves. And we have the corresponding control design consisting of those same objects. Analog sensors for horsepower, level, temperature, and pressure, 2 motors, and 2 valves. The design is easy to create, easy to maintain, and easy to understand. Because it mimics the layout of your plant itself, if you understand the plant, you automatically understand the control. Plus, systems built from self-contained and self-reliant blocks can themselves become self-contained and self-reliant blocks in a bigger system. The complexity stays constant as your design grows instead of growing exponentially when you try to scale traditional PLC programming techniques. Life is simply easier with object-based programming. So with object-based programming, adding a sixth carousel to your airport baggage system should be as easy as 1. Declare your new carousel function block instance, call that instance, add the new carousel visualization block instance to your master visualization, connect the visualization block instance to the function block instance, configure the new function block instance in your CSV file. So here we have a carousel 6. Then its 3 parameters. The carousel needs to know what type it is. Apparently there's 3 types of carousels here. What the IP address is so the I/O can reach it, and then some other configuration variables. Here we have the maximum speed of that carousel that it's allowed it to go. That's it. No adding variables to a program list, no copying programs or visualizations, no modifying programs with new global variables, no mapping new variables to new visualizations, no adding items to the unit conversion lists or the persistence list or the recipe lists or the log lists, no mapping individual tags to the I/O, and if you also use object-oriented alarming, there's no adding items to the alarm manager. Alarms for the new carousel just begin to appear magically. No human intervention or manual processes required. No muss, no fuss, no mistakes. So once it becomes this easy to add a piece of equipment to your design, you have reached the apex of object-oriented industrial programming. You have become a grand poobah of OOIP. So let's review why traditional PLC programming techniques are incompatible with object-based programming and do not promote reuse of your code. Say we have a plant which has 2 reactors, and each reactor has 2 augers, and each auger has a variable speed motor and a shaft encoder. And let's say that we hard code the discrete input of the shaft encoder to the I/O point at slot 1, pin 1. And let's further say we hard code the size of the auger to 1,000 pulses per liter. The problem is that the discrete input configuration values are now hard coded for all 4 shaft encoders in the plant. So 2 in reactor 1 and 2 in reactor 2. All 4 inputs are tied to the same I/O point. So obviously that's not going to work. So the only way around this is to make 4 copies of the auger and hard code each discrete input into each copy. Then we would need to make copies of the reactor, each hard coded with its copy of the auger. Nothing is reusable. We have a ton of complexity in duplicate code. And when we have duplicate code, it's guaranteed that one will be improved or fixed and the others won't. You're guaranteed to get a call on Christmas Eve to fix a bug that was fixed once or twice before, right? It's inevitable. So CODESYS provides a way to address the I/O issue. The I/O point can be mapped into each instance as appropriate using the full path names as shown here. So here we have the application .plant, the plant, R1, reactor 1, A1, auger 1, SE1, shaft encoder 1, pulse underscore FI. So it's mapped to that pin in this instance of this auger, in this instance of this reactor, in this plant. The second discrete I/O point is the same, except now you'll see it has A2 instead of A1 to go to the second instance of that auger. Then we have the same thing for the second reactor, the 2 augers in the second reactor, except now it's R2 instead of R1. Unfortunately, CODESYS doesn't have something similar for handling configurations, but I have a workaround called the CPP library. It creates a spreadsheet with a section for each equipment type. Here we have a shaft encoder with a row for each instance of that piece of equipment. So here we have a row for each shaft encoder, and each shaft encoder has its own specific sizing. pulses per liter. 1,000, in this case 2,000 for the second one. The auger and the reactor are now totally reusable. 0 duplicate code, 0 lists to maintain, or arrays of pointers, Excel macros, or any of the other tricks we used to use to create reusable code before the language gave us built-in capabilities. So there may be 50 ways to leave your lover, but there are only 6 ways to map your I/O, or at least 6 that I have discovered. Each has its own advantages and disadvantages, and I'll go through each in the next set of slides. The first is mapping from the program to the I/O device. This is where you hard code the I/O point into your program. This can be done with the old memory mapping technique we used in the era of disco and leisure suits, or it can be done using the new feature CODESYS just added where the full path to the I/O point can be specified in the program. Not sure why CODESYS added that. Apparently they must have an influential customer who loves disco and leisure suits or something like that. Who knows? Anyway, the biggest disadvantage of this is that mapping is buried in your program. So anytime you want to remap your I/O, you've got to go change your program, which is not usually a good idea. The chances of making a mistake are quite large. The I/O can't be added or remapped without shutting down the process. And of course, this is incompatible with reusable programming like we saw earlier. And the only advantage I can think of is it's conceptually simple for small designs or for beginners. Now, note that the arrows here represent the direction of the mapping, not the direction of the data flow. Obviously, input data will flow one way and output data will flow the other. So in this, the head of the arrow indicates where the I/O mapping is specified, and the point indicates where it is mapped from. The second technique is the global variable technique that became popular in the 1980s. This is where all your I/O is mapped to global variables, and then your program hard codes those global variables. This has the advantage that it does provide a central location that can be used to remap your I/O, but you still can't add or remap your I/O without shutting down the process or your plant. It's incompatible with reusable programming, as we showed you earlier. Plus, this one takes double the CPU time to copy each I/O variable twice on each process cycle. And plus, you've got the time and effort to maintain these lists. You've got to maintain the global variable list. If you add to your program, you've got to go and add variables to that global variable list, and also the CODESYS I/O tree. If you add more I/O, you've got to go modify and maintain that CODESYS I/O tree. So this technique is definitely an improvement over the older techniques, but still leaves much to be desired. The next is what I showed you earlier, where the I/O is mapped directly to the instance within your program. It provides the bare minimum to enable code reuse using object-based programming. But now we've lost the central point of I/O mapping, and it still can't be modified without shutting down the plant or equipment, and it requires millions of mouse clicks or custom automation to export, modify, import the CSV files from each module or whatever other technique we use to try to simplify that process a little bit. The next technique uses the first of the cognitive leaps we talked about earlier, where an I/O module is just another piece of equipment, just like any other piece of equipment in your plant or machine, and is treated as such. So notice that there is now a function block for each type of I/O module, an IFM 2016 in this case, and that function block is instantiated in the application just like any other piece of plant or equipment. Now obviously, in a typical plant there would be dozens of different types of I/O modules and hundreds of instances of I/O modules. We're just showing one each here to keep the example simple. So the I/O is mapped from each I/O module instance as a blob, and then the I/O function block instance maps the I/O to each piece of equipment using full path names. This gives us back our central point of I/O mapping and now allows for another cool feature. Visualization blocks can be created for each I/O module. This allows visualization screens to be built that show exactly what is happening at each I/O module, provides the ability to see what piece of equipment is mapped to each I/O point, and allows the I/O to be overridden for testing and maintenance. But it still has the downsides that it requires maintenance of the CODESYS IO tree, maintenance of the IO function block mapping list, and it also has this double CPU time copying the IO values twice for each process cycle. The next technique uses the second cognitive leap that we talked about earlier, that the IO mapping for each piece of plant or machine equipment is just another parameter for that piece of equipment, just like the set point for its high alarm or the auger size as we saw earlier or whatever. Notice in this slide that a configuration input has been added to the motor control called start port map _ CI, and its value is assigned in the IO mapping CSV file. So here we have the M1 instance of the motor control has a start port map parameter, and that is tied to the motor cabinet 1 port 5 from this instance of the motor cabinet 1, which in this case happens to be an IFM 2016. So here we're showing a CSV file, but it could just as easily be assigned in a company SQL database or an engineering planning tool like ePlan, or wherever else your team manages the design of your plant and equipment. In this example, we're using the ControlSphere parameter and persistence library, the CPP. The CPP finds all the instances of objects within your design that have configurable parameters and then creates this file for you. You then modify the file with the actual IO mapping, as in C3 here, and then you read the file back to implement the IO mapping for all your devices. This file is automatically read in on startup, so your project is always properly configured, or could be reread at any time to dynamically change the IO mapping in your plant, or the IO mapping could be changed by your program without even involving the CSV file or the IDE. So say your plant has redundant sensors. If one fails, just programmatically change the start port map _ CI variable and trigger the OOIO library to execute the change, and then your plant is automatically using the new sensor. Or say you offer multiple variations of the machine you mass produce, and each variation uses different IO mapping. Just set up a CSV file for each configuration and have the OOIO library read the appropriate CSV file for each variation that comes off the production line. No need to maintain multiple different programs or involve the CODESYS IDE for each variation of machine coming off the production line. The I/O is then bulk connected to the I/O function block as in the previous approach, but in this approach the mapping is made from the equipment into the I/O function block via an equipment parameter, start port map _ CI in this case. So we've got our central point of I/O mapping back, CSV file, SQL database, whatever. You can remap your I/O without shutting down the process. Unfortunately, you still can't add or remove I/O without shutting down the process, but it is compatible with reusable programming, object-based, and it allows a cool I/O visualization, but it still requires maintenance of the CODESYS IO tree and the CPU time to double copy each variable on each process cycle. The last and ultimate technique uses a third cognitive leap I asked you to consider and throw out the old CODESYS IO tree entirely. This is the same as a previous technique, except now each I/O function block communicates directly with the I/O. The time and expense of setting up the CODESYS IO tree and the CPU time spent copying the data twice is totally eliminated. The advantages are the same for the previous technique, except now the CODESYS IO tree has been eliminated. Not only can the I/O mapping be changed without editing the program and shutting down the plant, I/O modules can be dynamically added without editing the program, shutting down the plant, or involving the CODESYS IDE at all. Now the production variation in your machine can even include different sets of I/O modules. Plus, you no longer need to deal with the CODESYS IO tree, the millions of mouse clicks to configure your IO or create and maintain Excel macros or some other outside tool to modify the CSV file you exported from each IO module. Just place your IO modules in your program, configure them all in one place, CSV file, SQL database, or whatever, and you're done. However, this has the one drawback: the IO vendors or a third party must create function blocks for accessing their IO. This has been done for all Modbus IO devices by this company selling this product on the CODESYS store, but we're still waiting for some IO vendors to provide that function block to do that for other types of IO and IO protocol. So in summary, hard coding IO in the program has very few redeeming qualities, except it's simple for beginners and small applications. Using global variables provides a centralized remapping point, but has many other disadvantages. Using the CODESYS full path mapping technique is compatible with object-based programming, but now we lost our central point for IO remapping. Mapping through an IO function block brings back the central point and allows the cool IO visualization, but it still requires messing with the CODESYS IO tree and has some other complexities that I haven't mentioned here. Treating IO mapping as equipment configuration solves many of these problems, but you still can't change your IO without shutting down your plant, and it still requires messing with the CODESYS IO tree. The ultimate solution eliminates the entire CODESYS IDE tree altogether. Its only drawback is that it does require a way for the program to communicate directly with IO, and we're still waiting for some IO vendors to provide function blocks to do that. So let's look at the ultimate solution in practice. This is a design for the automation on a large racing sailboat. It includes some services, some hydraulics, winches, cylinders, and IO modules. Pushing into the cylinders, we see all the instances and variations of the cylinders used on the boat. Pushing into the IO modules, we see all the IO modules of several different types. The IO mapping for the entire project is done in one centralized CSV file or SQL database. In this case, the position_FI field input for the Genoa sail is mapped to pin 5, port 2 of IO module 12, the CR2050 in this case. So just place your equipment objects, both your traditional plant equipment and your IO modules. Configure your equipment, including the IO mapping for each piece of equipment. Place and link your IO visualizations, and you're done. No adding variables to the global variable list, no copying programs or visualizations, no modifying programs to global variables, no mapping new variables to new visualizations, no adding items to the unit conversion list or the persistent list or the log list, no mapping individual tags to the IO, and no adding items to the alarm manager. No muss, no fuss, no mistakes, no bugs, because you're reusing objects that you have used and proven in the past. And if you do this, it begins to look like the apex we talked about earlier. You have become the grand poobah of object-oriented industrial programming. So at risk of completely blowing your mind, Technique 6 could be taken one step further, where the equipment specifies the IO type and the engineering units it requires. The equipment needs are then provided to the IO configuration CSV, and the IO then specifies how to deliver the requirements. It specifies some mapping to the IO point, the scaling needed to deliver the required engineering units, and any other IO configuration that's necessary. For instance, if it was a universal IO, where it could be an analog in or an analog out, or discrete in or discrete out, or whatever, this is where that information would be specified for that IO point. This is really a perfect division of labor. Each object provides information that's germane to it. The equipment tells the IO what it needs, and the IO sets itself up to provide what the equipment needs. So now this example shows the I/O mapping being specified in the I/O module instances, but that part of it could just as well still be done in the equipment, like we showed in version 5 and 6. So whichever you prefer, it works either way. So in summary, the advantages of object-oriented I/O. So it supports object-based programming. Function blocks can be created and used over and over without ever copying code, renaming variables, creating and maintaining global variable lists, or any of the other tricks we used long ago to implement object-based programming before direct language support became available. So, I don't know if there's anybody in my audience here old enough to remember the tricks we used to do to implement object-based programming in C before C++ came along to make that easier for us. We used to create arrays of elaborate structures and pass those arrays between various C subroutines. We would also create Excel macros to help us create the code we needed because there was a lot of repetition. And of course those macros would get lost and would need to be recreated a few years down the road when the program needed to be modified or enhanced. I occasionally see some of these exact same techniques used to implement object-based programming in CODESYS without using the object-oriented features 6.1131-3 now provides. It certainly works, but as we learned in the C days when C++ came along, it's much simpler and easier to use the features provided in the language. The second advantage, no need to create and maintain global variable lists or maintain the CODESYS I/O tree. It eliminates the endless mouse clicking to configure and map your I/O via the CODESYS I/O tree. It also eliminates the need to create and maintain custom automation to modify CSV files exported and imported from and to each I/O module. And then, of course, rewrite those macros a few years later when the originals are lost, or when someone else takes over the project and just finds it easier to rewrite the macros than to understand how the original ones worked, because obviously they were never documented, right? Nobody documents anything in software anymore. The third benefit is that all I/O is efficiently mapped in a single location. This location could be a CSV file, a company design database, or plant planning tool like ePlan. And the fourth is that I/O can be added or modified without shutting down the plant, or without the need to invoke the CODESYS IDE at all. I/O can be modified programmatically and or through a visualization, or different predetermined sets of I/O configurations can be swapped in and out without involving the IDE, thus allowing any number of product variations to be accommodated with one single CODESYS project. No need to try to maintain multiple variations of a project. So that's it. I hope that makes some sense. There will be an example of this on the OOIPfoundation.org website, and please ask some questions during the Q&A. But before I let you go, while I have you here, I just want to remind you that the book of CODESYS is available. It's a large book, 8.5 by 11, hardbound, almost 200,000 words, 492 pages, full color pages, and it's by far the most comprehensive source of CODESYS information in one place. So go to www.bookofcodesys.com for information on how you can obtain that book. And for those who prefer interactive training, the 4-day CODESYS intensive training is available. Check the CODESYS website, or just send me an email at gary@controlsphere.pro. The curriculum for this training is also available for those who want to get in on the ground floor of the CODESYS device independent revolution and teach your own classes. Very quickly, the CPP library that I mentioned earlier is available in demo form right now, a beta form on the OOIPfoundation.org website. And it will soon be available in the CODESYS store. CODESYS is having some issues with their store right now, but hopefully they'll get those resolved soon. And finally, I encourage you to check out my object-oriented industrial programming playlist on YouTube. Just go to youtube.com/@ControlSphere, and while you're there, please don't forget to hit that subscribe button. So I hope you have enjoyed this Tech Talk. If you're interested in more information on object-oriented I/O, just drop me an email at gary@controlsphere.pro.